So, hello, doctor. My name is Huang Yuming, and my matrix number is GS72824. And my text is about project 2 and project 5 and project 8. So, I'd like to briefly introduce about the simulate inter-arrival time of events using the exponential distribution. That is widely used in communication system and queuing series. So back to the project 2. Let's run the code first. And we can see that the result of this code running means that the interval time between the arrival of each task. So back to the code, we send a arrival rate variable equal to 20. That means that on average about 20 packets arrive every second. So roughly one packet every 0.05 seconds on average. So what we want to do is generate a random number that simulates those arrival intervals with an average of 0.05. So then we use the loop to generate these random intervals. For that, we use because we import the random first, and we use the import variate functions. This function doesn't produce a truly random number, and it means that the random number is not a truly random number, right? It's random with limit, but it's follow the exponential distributions, which is great for the modeling time between arrivals. So we just pass in the arrival rate as the parameter, and the result we keep 4 decimal places. So that's all about project 2. So about project 5, this code is used to simulate random numbers using a method called linear congressional generators, or LCG for short. LCG for short. In this method, A is the multiplier, and B is the number we add each time. That is increment, the increment. And we use a very, very big number, so it can keep the randomly, right? And N is the modulus that keep the result within a certain range. And this line create a starting CX that change every time that you run this code. So that's a loop, also a loop, and we will run 1000 times. And this formulation is a LCG formula to generate random number. And this line take the generate number and turn it to the decimals between the 0 and 1. So that's called normalization, right? And this part of code just draw a scatter plot of the random numbers, and L goes to x-axis, and the index goes to the y-axis. So there we run this code. Oh, you can see the result. It generates 1000 random numbers using a LCG method, and normalize them to fall between the 0 and 1. So then it plots this varied as a scatter plot. So you can see that on the x-axis, you can see the random numbers. Each one is between the 0 and 1, right? 0 and between 0 and 1. And on the y-axis, is simply show that the index of each varies between 0 and 999. And you can see the spread and the randomness of the generated values. So if the point look very evenly spread across the x-axis without any obvious patterns uh, or something, that means the random number generator is working very well. So the next code is simulating the random amount of time between the events, like how long you might wait before the next text showed up or next text arrive in line. So first we use the export variate to generate a waiting time. It's just give us a random delay, like how long we have to wait for the next event, right? So um so uh the PDF is about when something is most likely to happen, and the CDF is about how likely is that it's already happened by a certain time. So back to the formulations about the PDF. A PDF basically shows us how likely an event is to happen at a specific moment. So for example, if you are waiting for a bus, the PDF might tell you that it's more likely to arrive in the next few minutes, and less likely the longer you wait. On the other hand, the CDF, which is just is the areas under the PDF curve, right? It tells us the total chance that the event has already happened by a certain time. So in the bus example, the CDF will tell you something like, there's a 17% chance the bus have arrived within the first 10 minutes. And we calculate the means and the variance. And the following code is used to plot the PDF and the CDF graph. So then we run this code. So that's the result, and you can see that this graph is about the PDF, and this graph about the CDF. So that's all my project. Thank you, Doctor.